champ.
Hey, you talked to Mark lately?
I haven't really talked to him, but he looks pretty down.
He looks pretty down. Yeah, well, maybe we should cheer him up then.
What do you suppose we should do?
Well, does he like butter tarts?
I was lying on the grass of Sunday morning of last week, indulging in my self-defeat. My mind was thugged, all laced and bugged, all twisted, wrong and beat. Uncomfortable, 3 feet deep. Now the fuzzy stare from not being there, a confusing morning week, impair my tribal lunar speak. And of course you can't become if you only say what you would have done. So I missed a million miles of fun. I know it's up for me,
If you steal my sunshine,
making sure I'm not in too deep.
if you steal my sunshine,
Keep me bursting on my feet.
if you steal my sunshine,
Champ, come here.
Wow, look at her.
I know.
Man, I've never seen Sharon look so bad before.
I did once before, but this is pretty bad.
Yeah, what do you think she got up to last night? Sharon! I love
I was flying on the bench, sliding in the park across the street. LATER that week. My sticky paws were in the making straws out of big fat slurpy treats. An incredible Lakewood heat. Now the funny glare of pale gleaming tear and staring underneath, involved in unusual feet. And I'm not only a monk, but I invite who I wanna come. So I missed a million miles of fun.
I know it's up for me,
If you steal my sunshine,
making sure I'm not in too deep.
if you steal my sunshine,
Keep me bursting on my feet.
if you steal my sunshine,
I know it's done for me.
if you steal my sunshine,
Awesome and hard to see.
if you steal my sunshine,
Keep me dumb and built to beat.
if you steal my sunshine, my sunshine, if you steal 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 my
Please don't go. 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 Babe, I love you so. Please don't go. And I want you to know that I'm gonna miss your love. The minute you walk out that door. Please don't go. 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 Please don't go.
everybody, or it may be morning or evening or some other time of day where you happen to find yourself watching us today. My name is Brad Keeler. I'm the director of the Geo-Institute, and this is GeoStrata Extra. In the summer of 2020, we started doing this as a supplement to our magazine, which comes out 6 times a year. If you don't know anything about it, you can head to readgeo.com and check out the current and past issues. What we wanted to do is sort of a behind the article where we have one of our authors from the current issue join us, and they're interviewed about their article. You'll find out things that didn't make the cut into the article, maybe some of the background of why it was written, and so on and so on. And for that, we are grateful that you are here. If you don't know anything about the Geo-Institute, you should, well, after you watch this today, you should head over to geo-institute.org, and there you will find out that we are a technical society with about 12,000 members, most of whom are geotechnical engineers and or geologists, and that we are part of the American Society of Civil Engineers. And of course, if you like what you see today, and I'm feeling good about this one, you should click like, subscribe, get notifications, and we will let you know every time we post something to the YouTube channel. A few notes. You'll notice behind me is a Guy Fieri version of Yoda. Today is May the 4th, and about 10 or 12 years ago, some very wise internet person decided that May the 4th should be a Star Wars day, and people should go around saying hilarious things like, "May the 4th be with you." And so, dear viewers, I offer that to you along with Yoda in mirrored sunglasses today. The other thing I will say is if you do not yet have your Carl Terzaghi bobblehead, head over to geoinstitute.org, make your contribution to student programs, join the 96 Club. 100% of it goes to the students and 100% is tax deductible. And we have brand new GI socks as well with the shield. They are lovely. They look great. They're suitable for everyone. And they're great as a gift. So you might want to consider picking those up too. So we are currently in the April-May cycle of GeoStrata, and that issue, as you may recall, was all about remote sensing. And so that's what we bring you today. And here to introduce and to conduct this killer interview with Dimitrios Zekkos from the University of California is GeoStrata editor Gizem Bozkurt from GeoSyntech. Gizem, the floor is yours. Run the show.
Thank you, Brad, for the introductions. Welcome, everyone, to the current edition of GeoStrata Extra featuring April-May issue themed "It is Remote Sensing from Far." I'm holding my magazine, which I received 2 weeks ago. I hope you will all enjoy while you read it. So, as Brett mentioned, my name is Gizem Bozkurt, Senior Engineer with GeoSyntech Consultants in Atlanta, Georgia, and I will be your host today. I have been an editor since January 2020, but my involvement with GeoStrata started when I was a PhD student at University of Wisconsin-Madison. I serve as GeoLegends Committee Chair for almost 2 years and work with student authors of GeoLegend articles and coordinated GeoLegend series with magazine's editorial board. For those who didn't have a chance to read the latest issue, Mohammed Gaber, Distinguished Professor of Civil Engineering and Construction at North Carolina State University, was the featured GeoLegend. So today, it's my pleasure to introduce and interview Professor Dimitrios Zekkos. His commentary piece titled "There is an Exciting Future Ahead," and a big chunk of it will be remote, was published in this issue, and today we are going to talk about it. An introduction about him: Dimitrios is a professor in the Department of Civil and Environmental Engineering at the University of California at Berkeley and licensed professional engineer in California and Greece. He has 20 plus years of experience on integrating field characterization and monitoring data to characterize the response of infrastructure and geosystem, with a particular emphasis on natural hazards and environmental sensors such as climate change. He has been using integrated approaches such as that leverage satellites, unmanned aerial vehicles and in situ data collected using wired and wireless sensors. He has published more than 200 scientific publications, and his research has been funded by the NSF, NASA, World Bank, USGS, Michigan Department of Transportation, and private organizations. His work has been recognized by ASCE through several awards, including the Middlebrooks Award, Collingwood Prize, Casagrande Award, as well as the Shamsur Prakash Research Award and the Outstanding Innovator Award by the International Society for Soil Mechanics and Geotechnical Engineering. Before we start, during the interview, if you have any questions for Dimitrios, please type them in the comments for this video while you watch, and we will do our best to address them as time allows. Okay, welcome, Dimitrios. First of all, how are you?
Great. Hi, Gizem. Thank you so much for having me and for the honor of having me interview and talk with me. So it's a pleasure to be here.
Thank you for joining us. So how is your sabbatical leave in Greece going, and what are you working on while you're away from Berkeley?
I'm enjoying my sabbatical. I'm mostly based here with my family in Greece for the sabbatical. It's finishing in next month, basically. So I'm planning to be back in California. I look forward to being back in California. It's been a fun experience for the whole family, and from a scientific perspective, I've been trying to push further my research agenda in terms of this type of things, in specifically focus on data analytics and doing more work in that direction. So it's been I've been studying a lot to gain even more expertise in that direction.
That's cool. We're excited to hear more from you. So I guess we can go ahead and get started. I have two questions to start with. They're kind of related to each other, so I would like to ask them both at the same time, and you can take your time to answer them as you see fit. So the first one is, what are the major technological advances in remote sensing in the last 20 years since you have been part of the geotechnical engineering community? And can you briefly talk about the advances in autonomy, such as robotics, sensing, and controls, and how these technologies have been and will be used by geotechnical engineers?
Yeah, absolutely. And so in the last 20 years, I think there has been a lot that has happened. I will start with something that has actually, I think now has been integrated in practice, which is the remote data transmission of wireless sensor, or wired, but also wireless. So the idea that you can actually now put a sensor and embed a sensor piezometer or inclinometer or something, and the data is transmitted there. We don't typically think of that as remote sensing, because we're in remote traditional sense of remote sensing. We're thinking measuring something from far, from like a satellite or maybe UAVs. But this is also definitely a big part of geotechnical engineering. And I think there are a number of companies now that provide this type of service, which is really, really useful. And so that definitely has happened. And I will say it's part of our practice now. You can do that, you know, and so that's the first. The second, on the more traditional remote sensing approach, is the innovation we have on satellites. We started with Google Earth more than 20 years ago, I think, at this stage. But what is very, very important to explain is in the last decade or so, maybe even less, there has been a tremendous innovation on satellite technology. And so in terms of Earth observatories, satellites, maybe in 2013, we had about 150 satellites for the entire planet. And now we're more than 800. And so within basically a decade, we have 5 times more the satellites that we had before. And that is not expected to slow down. If you see the plans of these companies that are doing this, there's a lot of private investment in that direction. They have a very exciting goals of better quality data more often. Some of the companies have plans to be able to see the entire planet in high resolution 8 times per day. I mean, this type of innovation, if it happens, which I think it will, changes things on what we can do as geotechnical engineers in a big way. also into the future. You could monitor a construction site if you have 8 pictures per day with, just from satellites. And then, of course, definitely in the last decade or more, we have the UAVs and drones that basically, we're going to talk more about this for sure, but they have allowed us to see better and higher resolution and as often as we want. And I think that's a major breakthrough for our geotechnical practice. And so this type of innovation, I think, will continue. It's been now, you said, the last 20 years, but I think we're going to see the next decade will be super exciting from our perspective, for sure. Your second question was about autonomy. Can you remind me? Yes.
Yeah, so basically we would like to hear more from you about the advances in autonomy. Maybe can you elaborate more about the robotics, sensing and controls, and how these technologies have been and will be used by geotechnical engineers? Do you have any examples to share from your projects?
Yeah. Absolutely. And you're very right to bring in the autonomy in this, because actually I got into remote sensing through the autonomy part personally. But overall, I think there's going to be tremendous advances in introducing autonomy in infrastructure. I can share a slide, actually. I have a slide if you want. I can share with you.
Yeah, that will be amazing. Yeah.
Awesome. Yeah, let me find it here. So I have some random slides depending on what we end up talking about. But when we're talking about autonomy, I think we are talking about robots and satellites. We're talking about sensing, and we also talk about controls, meaning acting on that data. And I think this type of approaches, autonomous approaches, will change the way we're doing everything in infrastructure, how we operate it, how we build it, how we design it even, and definitely how we protect the environment. And so if you look right now, I think there are autonomous vehicles of different kinds, and on the streets, we see that. We have sensors put in infrastructure, maybe not at a huge scale, but definitely on the critical infrastructure. We have health monitoring sensors on our retaining walls, on our bridges. We have them on their storm waters. And then also we control energy consumption in buildings, HVAC systems through controllers like this. So this stuff is happening right now. And I think it won't be long that we will have autonomous construction. We already have semi-autonomous construction. We have, but I think we're going to have possibly fully autonomous construction in the not too distant future. And robots of different kinds. So everybody knows about UAVs delivering packages and people, I will say, but definitely packages. And we can easily envision robots really protecting our coastlines from erosion, and submarine robots cleaning up the water from microplastics or other contaminants. And so I think this is not going to be an afterthought, like, oh, let's do this because it will be cool, let's do this. I think this type of approaches will shape how we approach, how we manage risk, how we protect the environment, for sure. And robots are a big part of the autonomous future. And I have here different types of robots that we are using at UC Berkeley. Everybody is thinking of UAVs, of course, because those are the technologies that basically could be used by lots of industries. And so they became cheap, and they were cheap enough for us to integrate in a practice really quickly. And so I think that's why we have UAVs at the prices that we have, and we can use them. But I think we're going to see, and we're already seeing terrestrial robots collecting data, and definitely submarine robots collecting data underwater. And I think this will be super, super exciting, because what the robots do, it's not just that they're cheap and it's a new thing to use, is that there is a fundamental change in an add-on compared to what we've been doing. Robots allow us to have mobility in our sensing. So the traditional way is I find my most critical spot, I put my sensors there, and I monitor this. But in live systems, the most critical places may change. And so by having robots, you can monitor how the system is changing and really relocate sensors or start looking at other places. So the concept of mobility in sensing is, I think, groundbreaking for our infrastructure, especially large and distributed infrastructure. But also, we need to recognize that these robots are computers that can walk or can fly. And really, at the end, we can mount any sensor we want on them. And so, for example, here I have different cameras, optical that everybody knows of, but also there is infrared and multispectral, and there is LiDAR, which is a laser sensor for geometry. And we can even integrate geophysical sensors or gas sensors to them. So I think what we're going to do as profession is a function of the problems we're having to tackle. But all of these are sensors that we have integrated at UC Berkeley and we have used on different types of projects. So I think the idea of the autonomy in infrastructure is it's definitely a frontier that it's going to come quickly. It's kind of already here, but we're still at the very early stages of it. Yeah.
So you mentioned that you actually started working on the autonomy in this area. Can you tell us about the project you worked maybe a decade ago and how today's technologies could have improved the outcome in terms of speed, quality, quantity of the information you collected, and maybe safety in the field?
Yeah, absolutely. I was actually do have let me see here. This is a project I haven't, and I can describe it briefly, but this is a project that two of our PhD students have worked on, Will Greenwood and Hao Zhu. Will Greenwood works now for MATLAB and Hao Zhu works now for Tesla. And what you see here is a fully autonomous system. This is part of their PhD, a fully autonomous system where UAVs are equipped with geophones. They see each other, calculate the distance from each other, position themselves on a spacing that they decide, and then give a command to a mother UAV to pick up a weight and drop it on the ground to generate a stress wave. And then they pick up this stress wave with the geophones that are on the UAVs, process the data, and assess the quality. And give another command to the robot, to the mother UAV, to drop the weight or move on. And so this is like I think this is something that I've been doing seismic geophysics for a few years, but this is a place where now you can have robots go and collect more data, better data, and in places that we cannot send people. So here's a flat ground because that was part of the PhD, but you can imagine the system to be operating on top of landslides or on top of levees, or at the moon, right? And to really collect data about what the subsurface is. In this case, we're able to drop the mass at different heights and really generate stress waves and see 3 times deeper than what a conventional geophysical technique will do. So this is it's a relatively recent example. The students finished 2 or 3 years ago, just before COVID and during COVID. But I think it's an example of just a project where you can imagine if we were to release a system like that, you can collect data at a scale that normally you will not be able to afford because you cannot have people collecting more and more data. So this is just a very, very simple example of that. Beyond that, though, I got involved into this type of work through my work on post-disaster reconnaissance and failure analysis. So when you go to some of these places that are affected by earthquakes or storms, these are places that really don't have a lot of resources. And you also cannot have a lot of resources with you. You cannot carry too many things. And so as I was collecting data, I realized that a UAV, for example, could collect data at a much better scale, faster than anything I will have ever been able to do. And so the last, it's been now more than 10 years I've been working with UAVs to collect this type of information. So for disaster response, understanding data, forensic evaluations, you can have robots collect data at a scale that we could never afford it otherwise. And that data is going to be really super exciting for the future, because we'll be able to use that data to learn better. I have been going every year since 2015, almost every year, to Nepal. Nepal was hit by the Gorkha earthquake in 2015, and there was devastation. There were more than 25,000 landslides, affected communities, lots of people died. And every year since, and before actually, but definitely since, there is these monsoons that are hitting. So the communities are struggling to recover, because as soon as they try to repair some of the affected areas, there's another monsoon that comes and hits them again. And they are really trying to find better ways on managing the very high risk that they're subjected to. And so being in Nepal all these years, it's definitely, using robotics and remote sensing is definitely a place where you can actually collect data at a tremendously higher scale than otherwise. But it doesn't have to be, last thing I will say, sorry if I'm saying too much, I get excited about talking all that.
Take your time, yeah.
It doesn't have to be developing countries or places that are really affected by the disasters to where these robotics are really, really useful. I have here this video. Let me show you, share the screen very briefly. This is again from an affected community in Greece. There was an earthquake in 2017, and there are some in this community, and some buildings are damaged, some of them are not. If you look from above, only from a satellite, you may see some of these buildings looking good from above, but really some of the walls are missing. And most importantly, as these buildings collapse, they affect accessibility. You cannot walk on some of those roads because some of these buildings have collapsed on them. And so this is a footage from a 3D model from a UAV that basically you can really collect this data extremely efficiently within a day or two. We did it within a day and a half with technologies we have now, definitely within a day, process the data and use it for decision making, for how to really respond to the disaster and then how to restore it. Such technologies are really changing. There is no other technology right now that could have provided you this type of information, and definitely that quickly. And so that's part of the exciting part about being able to responding to disasters through this type of technology. I don't know if I answered the question.
Yeah, you did. I mean, it's really cool, and we can clearly see your excitement in this area.
Yes.
But my favorite question is, which advancement excites you the most and make you think that there is an exciting future ahead and we are just starting?
Yeah, I think overall as I mentioned, the autonomy is a very big part of what I think is going to happen. It's not about just the satellites. It's not about just the robots. It's about the data that we can collect. And when we collect this type of data, I think what we're going to see is that there is insights, things that we haven't noticed, that are not properly accounted for, they're not properly modeled, and we will need to address that. And so I think the synthesis of all of these together, the satellites and the UAVs and even the wireless sensors, is really, we will create new frameworks that we're not thinking. I think we're not really implementing them in practice. Yeah, so I'm very excited about contributing in that direction.
Yeah. And you also answered this question in your commentary, but if you would like to expand your response for our listeners, and you already touched base into this while you're talking or answering the previous questions, but are the major advances already made? So should we expect only incremental improvements from now on, or we are just starting and there is a lot to do in this area?
Yeah, no, absolutely. I mentioned that in the commentary. I think we haven't even started. I mean, all the stuff that I'm describing about happening right now is here, and we haven't really leveraged it. First of all, In terms of, I mentioned already the data. We're focusing a lot on surface data, and that's super useful, of course. And we're able to create 3D geometries and all that stuff and assess infrastructure. But I think robots will help us collect subsurface data. I showed an example of the UAVs in my case, but there could be terrestrial robots drilling boreholes. When people tell me about this being too far, I always talk to them about the CPT. The CPT is an approach by which you have a constant penetration rate. Sorry. And so what is happening there is the ground is changing, but there is enough capacity and a feedback loop that allows the penetration of the CPT to go at a constant pace. A robot will do that. Right now, of course, so the CPT is fully autonomous once in place. I will not be surprised, and I expect fully that in the future we're going to have lots of CPTs doing a lot of that on their own in places that we wouldn't dare for us to go. And so that's an example of something that's happening right now that I think we're going to see a lot more, going as far back as the CPT, and but that also being going to the next level. I do think also that I mentioned that before, that as we start collecting this data, we will see deficiencies. I can mention an example for a project in Michigan. When I was at the University of Michigan, we put our sensors there on a retaining wall, on a number of retaining walls. We had a technique by which we were looking at retaining walls along a highway for very large lengths, and then we put our sensor somewhere. Well, anyone who has done this and has looked at the data, you see the sensor, you put tilt meters, you put temperature sensors, we put and what you see is that the wall is moving every day and every night, day and night, and it will end seasonally. And the type of things that we're teaching in school, where there is a static wall that is not moving and nothing is happening, is not real. The wall is moving, is breathing. And now you may not want to model that, but sometimes when you have a wall moving a quarter of an inch due to this seasonality, I think some people will be surprised. They will not expect that. They will think that the wall will not move that much, but it is in some cases. In the case of Michigan, of course, we had also very high temperature variations and snow, and so the wall was moving a lot. And so now if you try to say, okay, I'm going to create a model to capture that, well, most models don't capture thermal effects. Constitutive models. It's, if you take a play traditional sense, the way it's implemented in practice, some of these things are not captured. So I think we're going to start, not only we're going to have a new generation of data collected, but a new generation of models that can satisfy, can actually model the things that we're seeing in practice. And so it's going to permeate throughout the practice, not just the sensing part. I also think that there is a lot that we will be doing with visualization. Sometimes as engineers, we design something, we explain how it's going to be built or how it's going to look, or maybe the consequences of some failure, and you take it to a client or to a stakeholder and they don't see it, they don't understand what you're telling them. And so I think with all this type of data we're collecting now, we will be able to communicate better to the stakeholders. And I think that's very, very important in terms of managing risk and really making sure that people make the decisions, good decisions with that. I do have a video on some of these models. So I mean, if you don't mind, I'll share again. I have lots of windows open here. So this is a video that my colleague John Manusakis has developed as part of one of our projects. And what you will see here is basically a rockfall. Now that rockfall happened during the Lefkada earthquake and detached during the earthquake and traveled 800 meters. And at the end really reached the bottom, a house, and killed one person. 2 people died from that earthquake. 1 person died from that rockfall. And so we deployed with the UAVs and collected the data. So what you see here is a visualization of really the rock bouncing around. And what you see in the terms of the bounces, it's not a movie. It's based on a numerical model that has matched the field observations. So it's not just a random rock like the way you will see it in the movie. It's actually a physics-based analysis. And so what you can see here, the rock, hopefully you can see it if it's not very, the rock is bouncing around and traveling, and everywhere that it bounces, it's actually real. So you can simulate really what happened in the past and use that, of course, to communicate in the future. I can pause the video here, for example, because what you can do if you collect this type of data, you can have a 360 view of really what the rock is doing and where it's been. Here is we're intersecting a road, and communicate exactly to anyone, because maybe there's a house next to it, or that really someone may not be able to see. And you can see that information. So here it's penetrated. So this type of communication, I think, can help us a lot with our decision making. Beyond that, and I don't know if you want me to talk about that at all right now, but I think the integration of the systems, the integration of the various sensors together will create frameworks that are really, really useful for us. I have here an example of, sorry, let me show this. So here's, you can have these frameworks with satellites, UAVs, and wireless sensor, and one fits the other. In the satellite, you can see very large areas. You can have lots of different sensors. It could be optical, it could be radar. INSAR is used extensively now, I think. Then you can have UAVs and collect the high resolution data that you cannot with the satellite, at least not right now. And then put your sensors in the places where you think it's most important. Here's an application of that. How this framework like that could work. So this is a road that is along this coastline, and you can have satellite-based imaging collected every day or INSAR, but here's with optical. This is an example of a photo of satellite before, after, and you can do manually map landslides like we did in this earthquake, but you can have also machine learning algorithms being trained to detect with some error, but really detect activity. You can use this information and really collect not only 2D data, but 3D. So what you see here is a picture of a coastline where we have a before and an after 3D model. And these are all the landslides that are mapped. And you can, wherever you see blue is loss of elevation. And when you see red is gain in elevation, because debris from the landslide came from the blue to the red. And once you do that, and you have this information, you can run a model. So here is all monitoring. This is data collected. Now you bring a model, and the model in this case is a regional model. It's a 3D model that is actually, you're running analysis at this 3D model, calculating, for example, factors of safety. And this is a schematic showing it, that a distribution of factors of safety. And then if you have an infrastructure in that, like a road or a water distribution system or something, or houses, you can create analysis plots like that, like, for example, length of roads as a function of factor of safety, and find the worst places, the roads that are the lowest factor of safety and most critical to your system, because maybe the road is not very critical to your system, and do more monitoring, put your wireless sensors there, or deploy more often, or mitigate. And so this type of approaches is, again, part of things that we will be working on we've done it in this project, but I think we'll see a lot of that happening for sure. Yeah.
Thank you so much for providing these details, and I'm really sure our listeners are interested in this topic. So I know that there is an upcoming short course that you will be giving. The course title is Introducing New Technologies for Geotechnical Infrastructure Sensing and Monitoring. Can you please tell us how our listeners can sign up for this course if they're interested in?
Yeah, absolutely. I will say first that this is a course, thank you very much for this. Actually, I'll be glad to talk about it, of course, because we're doing it on Monday, Tuesday, or online. And actually, people can sign up up until tomorrow if they're interested. They can go to our Berkeley website and find the information about the short course. But what we have in Berkeley is a number of colleagues that are working in these areas. We have Kenichi Soga, who has been doing a lot of work, fantastic work on fiber optics and wireless sensing. We have Dimitrios Zekkos working with UAVs and with levy applications and seismic applications, collecting lots of data. Rob Kayan, who is using INSAR, UAVs, LiDAR sensors. And so we have a lot of people and students, of course, because the students are always doing the research behind the working in these things. So we decided to put a course together, very practical for the industry, that communicates this type, the advantages of these technologies, and in a very practical way in what type of projects they have been used. So we offered that 3 years ago, and since then we've been offering them every year, and now we're offering it again in May. The whole effort is very integrated. We work very nicely all together. We have established also a Center for Smart Infrastructure at Berkeley that was funded originally by East Bay MAD and still is, but also others, that plans to really bring all of these technologies within the infrastructure world and really advance the profession. Because the truth is, for distributed, especially for distributed infrastructure, and what is distributed infrastructure? Roadways, tunnels, levees, even dams as kind of distributed. Some of them are really, really big. And I mentioned levees, of course, coastlines and large regions for sure. These type of tools are really well tuned. I forgot to mention, of course, water distribution, which is the interest of East Bay MAD, as well as gas line distribution, lifelines in general. We had a tendency as geotechnical engineers to have some, I wouldn't call it qualitatively, but some broad basis by which we identify the weak spots and then fix those. But these technologies allows us to start with the system and stay with the system until we find the weak spots, and really at the same time always assess the impact of these weak spots within the system. Because in many cases we cannot fix everything all the time. So it's really a very important decision what you fix first, and that's where all these approaches can help you a lot, in my mind. I do want to mention the course also finishes with digital twins, which is very much related to remote sensing. And in digital twins, this is where it all comes together. The data collected by these approaches can be overwhelming. If it's not overwhelming in the first time you collect it, it's going to be the second time you collect it. If you start repeatedly deploying with your UAVs or collecting lots of sensor data, you can have very soon a problem saying, oh, I have too much data, I don't know what to do with it. And so digital twins allows you to have an information about, it's a system, it's a digital replica of your infrastructure where all past information is collected, current information from sensors is being processed, and you can use that information also for the digital twin for simulations. We had created this picture here that I can show you of a levee, and that's a digital twin basically. So this is the levee, it's going for a long time, and it's the physical space, it's mapped by UAVs. But it's also a virtual space where you can have your finite element models or your limit equilibrium, doesn't have to be finite element, and it's all in one system. And then you have sensors, piezometers, inclinometers, fiber optics, and that data maybe is streaming data to you. And it's coming into this place, satellites and robots are collecting information, all of it is coming there, really being integrated, being understood. You can put the goggles and virtual reality and see the whole thing, and then say, okay, I understand now my system, let me run simulations, let me raise the water table in that system or the water level behind the levee at the high level and see what happens. And so you can really integrate the past, the present, and the future in these digital twins. I think digital twins will be a necessity for what the type of data we're talking about, unless you're doing it at a smaller scale. Yeah.
Yes, and the image just you showed is actually the one that your commentary, so the people will be familiar when they read your article.
Yeah, I use that in the commentary. I didn't describe it in a lot of detail, but yes, this was supposed to be explained that. Yeah.
I'm moving with the questions from our listeners. Can you address the gaps and weaknesses in the 360 3D modeling that you showed earlier?
The gaps and weaknesses?
Yes.
I think I will say that we typically don't yet collect a lot of that data yet, because I think I think number one of the biggest reasons is people are used to the way of doing things. I think it comes back from our training and how we learn things. We learn them a certain way, then this way works, and we're hesitant to change the way it works because we are worried about the consequences of doing something newer, but maybe we don't know it as well. I think so. I think there is the biggest thing about it is that you need to deploy some of these techniques. In this case, the one that I showed was with the UAV. And then I think that the weakness will be that you do need some more computing, meaning although you can collect really quickly data in the field, you do have to have computers to process this data. And depending on what you're doing, it could take a little time. I think in many cases it will be a little time, but in some cases it can take significant more computing capacity to do something more complicated. In this case, there's a 3D model, and then we use a 3D model to really back analyze what happened and really see exactly where the rockfall hit the ground and where it rolled. And then we simulate that with a model, and then we project that. So I think it is more like if you want to reach a level like that, it just takes a little bit more time in the office, but and you will only do it if you need it. I don't know that it has other weaknesses other than recognizing that once you have collected a lot of data, you have to process it and understand it. And you have to, data is one thing, knowledge is a second. You have to translate the data into knowledge, into something that, information maybe, data from data to information, yeah.
So there is one other question, seems like they are back to back. How sensitive is the image numerical solution to initial values? If we change slightly the initial values, may the final solution will change dramatically.
Of which what model are we talking about? Image or? Sorry.
I think he is not referring to, or the question, the owner of the question is not referring to a specific thing, but maybe can you elaborate a little bit more about the sensitivity of the image, the quality of the image, how that affects the results?
Yes. Okay. Yeah, so I think the technology now has advanced a lot, and depending on what you're trying to do, it may be adequate, it may not be adequate. And so I think, for example, always when we collect data, we need to be thinking why we're collecting it. Meaning that what's the objective? Let me say an example. You may, for example, create a model to get the geometry of a dam, or a geometry of a road, the embankment. Okay, and that could be perfect for what you need. So you deploy, you collect the data at some level, at some height, and all that stuff. Then if the question comes in after the fact and tell you, can you detect the cracks on the roadway or the cracks in the dam? The answer may be no if I haven't collected the data in a manner to see the cracks, which may require flying closer to the ground because of the specific camera. The resolution of the model is always a function of the camera that you have and how far you are from the target, in the case of the optical image, for example. And so we need to be thinking of this. I don't think, in my opinion, it can work in some cases, but in general, you do not easily just subcontract the decision of all this data collection to someone and say, bring the data, and then I'll see what I will do with it. There needs to be communication. That's why I think this is part of geotechnical practice. Now that, of course, you can have surveyors for that, but that they have to be part of the project, part to understand exactly why we're collecting and help you to collect the right data. One thing I would say, if there was a flavor on the question, if I understood correctly, about poorly defined systems. So for example, if something changes and then the result of the simulation may be completely different. I think that is, poorly defined system, numerical, not poorly defined, poorly constrained systems. It's a classic problem that we have. One thing I will say related to this is that because of the proliferation of sensors, we have an opportunity in some problems to really constrain that poorly constrained problems. We're able to collect data that will point us out to the right solution. And an example of that is in one project with my colleague Dimitrios Zekkos. We are collecting for levees, for example, data that is optical, infrared, electromagnetic, and seismic. Now, each of them on their own may not tell you what the quick spots is, right? Yeah. The optical on its own will not tell you about the subsurface. Resistivity is showing you weak spots, lower resistivity spots or high resistivity spots may tell you about something about moisture or clay content, but on its own, it's not very well defined. All of them together, you may start having a model, a subsurface model that fits all the data, and that may be actually closer to the truth. And we can collect that data now, much better than before.
Yeah. And by the way, she seems like added in the chat that she was referring to the rockfall model that you presented the video.
Oh,
yeah.
Yes. Okay. Yeah. So in this case, it's a for the rockfall analysis. Oh, yeah. There is a lot there. Okay. This is a very good point. With this type of data, so if you see what we were doing in the past, let's say before 10 years, in terms of rockfall analysis, everybody's focus was primarily on the beginning and the end of the rockfall path. That is not, okay, it's very important. We need to know where the rock is going to go. But now we can collect data about the rock bounces and whether the rock broke, for example, into pieces. Yeah. These type of things are not really modeled or checked against field observations. And if you have a good model, you will want to match all the bounces. If you start doing that and saying, okay, I'm going to do that, you get into details that are really, really important from a results perspective, for example, of the shape of the rock itself, circular versus some rectangular. That affects the kinematics and whether the rock is moving primarily or also rotating while it's mid-flight. Again, this goes back to the comment that I was making, that now that we're collecting this data, we may start saying, oh, I want a better model that captures this and this and this. But yes, absolutely, that's a great point, for sure.
And our last question is from our very own Brett Keeler, and he's asking, do you think we are moving towards a future where a lot of these technologies are custom-made for civil geotechnical work, or will they stay off-the-shelf products for a long time? Like drones, for example.
Yeah, no, I think what's happening in the case of for example, I showed the example of the UAVs doing the seismic geophysics, right? So the students achieved this. We worked very hard. We achieved this. Is there an immediate market for it? Can you sell this product, right? In reality, no, I will say there is not an immediate. Now, what we're doing at the university level is we publish our scripts, we publish our approaches, open access, everything. So maybe at some point, the jump for a company will be easy because the work has been done and they can make them actually use this type of information and create a company around it. But the truth is that many of these things require, there may not be an immediate market for them, but that doesn't mean we shouldn't push forward in that direction. I will say, though, the following. We cannot expect roboticists or aerospace engineers or computer scientists in the case of big data to come to us on their own to solve these problems. They will not. They will not solve these problems for two reasons. Their motivation is different. If you have a different motivation when you become a civil infrastructure person and you want to work to deal with natural disaster, and different when you go into computer science where you like scripts and you have different interests. And we are the ones who care about this problem, and we can bring that expertise. We can train our own students, work with computer scientists. Of course, we need them, and they need us to solve these problems. But it will not happen by someone outside of us, and we can take ownership of this. So I've been talking about the fact that I think we're going to see in the not so distant future. Now it's happening, in my opinion, because I have companies contacted me about this. The rise, what I call the rise of the geodata analyst. This is a geotechnical engineer who has training on geospatial data, understands 3D models, is able to process data at a big scale, from the sensors, and not really, through an Excel file, let's say, and really can pull all of this together. This geodata analyst is a geotechnical person. It's a geo person, it could be a geologist, but have a specific interest into this type of fields, into sensing, into programming. And we need these people. We want them in our companies for sure. Exactly as we had geoenvironmental engineering in the 80s, or maybe earthquake engineering started in the 70s and still continues, or foundation engineers. These are all people who are expertise in this direction. I think we're going to have this type of geodata analysts that will be a permanent staff in our companies, handling a lot of this data revolution that is happening, on how it's coming in, where it's going, who is analyzing it, and then using data analytics approaches, AI, machine learning to really understand it. It's not a small thing. It's a big thing that I believe is coming, and it's going to be really exciting. I think companies should not feel threatened by automation or autonomy. They should actually endorse it and bring it in their companies. This type of techniques is not threatening us. It's actually pushing us forward. It's diversifying us. It allows us to bring people that normally will not be in our company, and now they will come. And very, very importantly, it will bring young people who love this stuff. And normally we say, oh, I love creating apps and programming. I'll go to computer science and work for a tech company. No, we want them to say, no, this stuff, these exact things that you said you love, you can come and solve resiliency from earthquakes, battle climate change. And I think that's the proposition we're doing as civil geotechnical engineers. So it's actually very exciting to me, at all negative.
Exactly. I would like to thank you, Dimitrios, for participating and joining us today. I really enjoy our conversation. And I think we should ask Brad to maybe schedule a follow-up interview in 10 years so that we can see where we are and what are the advancements in these 10 years, so we can go back and, discuss all those future changes, I guess. Brad, back to you.
Thank you,
That'd
Gizem.
be great.
I think I forgot that all this will be on the record, and 10 years from now, I will say, oh my God, what I was saying in 2023. Yes. Yeah. Thank you very much for the opportunity.
You're off the hook with that, because nobody's ever right 10 years out. You can say whatever. Plus, you're lucky. That's what I say to faculty members, is you can say whatever you want. You guys can, give your opinions about everything, which I thought it was hilarious. I never ask questions.
Everything is recorded here, so.
And I put a couple in for you today because I was like, this is a great opportunity, because professors can give their opinions on anything, and they always have opinions. So I figured that was perfect. So thank you, Dimitrios, for a great interview today, and Gizem for facilitating it. You guys both did a fantastic job. Really engaging presentation, and it was really enjoyable. I do have a couple reminders for everybody. Today's GeoStrata Extra episode was sponsored by Tensar. They're a division of CMC. They provide engineered geogrid solutions for the stabilization or reinforcement of soil aggregates. When compared to conventional site development solutions, Tensar's technology-based alternatives are faster to install, incorporate higher performance, remain reliable over time, and are more cost-effective. You can learn more at tensarcorp.com. So thanks again to our sponsor for today. Again, if you liked what you saw, and you're here at the end, so hopefully you did, click like, subscribe, get notifications. We'll let you know every time we post something to the YouTube channel. Enjoy the rest of your May the 4th, and maybe watch a Star Wars movie or one of those animated series or one of the other 6,850 Star Wars properties that exist out there in the media world. Our next live stream is May the 15th it's May the 16th. I think I put the wrong one in the chat. It's part of the Keller Seismic Series. Armin Stuline from Oregon State University will be our presenter that day. So you definitely want to get more information and register for that. Hopefully we'll see you back here then. Sean Herpelsheimer was our producer today. Thanks, Gizem and Dimitrios, one last time, and we will see everybody back here very soon. I feel like unless we've got over 250 people in one of these things, you're never guaranteed that you're going to get any questions. And what happens usually is